Hi everyone, welcome to today's SF seminar. Today we have Zhuoqing Song from Princeton University who will present causal attention with Lookahead keys. This work introduces a need to it on causal attention, allowing keys to incorporate future information without breaking autoregressive constraints, which is very interesting. So with that, let's welcome Zhuoqing to start the talk. Please take over.
Thank you so much for your introduction. In this work, we focus on new attention mechanism. So let's first revisit the standard causal attention. To help explain our motivation, I first write down the standard causal attention in its recurrent form. As you can see, when we are generating the T+1 token, KT denotes and VT denotes the KV cache, which contains the representations of the first T tokens, which we already have. And the receptive fields of the keys in standard causal attention only, for example, the keys of token I only contains the information from token 1 to token I, with no information after token I exposed. For example, even when we are generating the 1 millionth token, the keys of the first token only contains information of itself with no updation. At this moment, we are not talking about like BOS token or attention sync. As a concrete example, for this classical garden part sentence, when we are generating the false token pass, the keys of and the values of token raised can only see the first 3 tokens. So now, I think most people will think raised is the past tense of the main verb, not a passive relative clause. So the keys of the token raised may encode the wrong information. As another examples, for example, humans often state the conditions first, followed by the questions. However, when we are solving math questions, we may first look at the question so that we can know which condition is more important. However, with causal masking in standard causal attention, models are unable to do this. It can only go from the conditions without knowing the questions. So it may waste some representation capacity on some irrelevant or unnecessary, unimportant conditions. And another example is coding task. There are many like we may assign values to some variables multiple times, but what really matters is the most recent value. However, in the language space, like x equals 1, x equals 2, they may be similar. So this may bring some noise in the attention scores. So despite these vivid examples, some papers have systematic analysis between bidirectional attention and unidirectional attention, and they show that bidirectional attention is usually better than unidirectional attention on natural language understanding tasks. And another thing is, for long context tasks, for example, we already have like 1 million keys. The directions of the keys may be distributed on the entire sphere. So in this case, no matter how we orient the query vector, we may have some keys which are almost parallel to the query. But this is just because we have limited head dimension, so we have a limited representation capacity. So this parallelism may be just accidental. So this can inject noise into the attention scores. And there are another indirect evidence that is for diffusion LLMs, we can use both unidirectional and bidirectional. But to the best of my knowledge, most diffusion LLMs are using bidirectional attentions. To overcome this shortcoming of standard causal attention on like sentence embedding tasks, there are some papers which want to, as you know, the most powerful pre-trained models are all uh, autoregressive. So to utilize this powerful pre-trained models and the advantage of bidirectional attention, some papers like backward dependence enhanced LM, they modify the last layer to be unidirectional, but keep the previous layers still they're still to be bidirectional, and the previous layers are still unidirectional to improve sentence embedding tasks. And echo embedding do it in a brute force way. It just duplicates the input so that the tokens in the second copy can see the entire first copy. So this is similar to removing the causal masking. And the rereading is similar to echo embedding, but it applies this method on reasoning tasks. Uh, Another related work is encoder-only next token prediction. They just stack the encoders to generate to do next token prediction. So as we know, KV cache is not available here. So its complexity is cubic in training, and and so this poses challenge in scaling the model scales up. Selected attention, they modify the attention matrix directly. But their focus is on filtering an unnecessary, unneeded context by seeing the information after the tokens. However, as we have discussed, in many cases, we need to actively incorporate information after it, like the garden path sentence. We need we and like the math problems, we put the questions after the conditions. We need to incorporate information after the tokens to inject after tokens to refine the representation of the keys. So it's uncertain whether this mechanism can do this task. Path attention is very close to our work because it also updates the keys in the inference, and it's also a rank one update. Path attention is primarily positional encoding. So I think it was further study whether we can combine path attention with our mechanism. And also, path attention is updating key, like updating kt by t minus one. So this makes the training process including a matrix inverse. So so path attention is primarily orthogonal to our work. So we may combine this together later. Yeah. So our approach is to expand the receptive field of keys and values. So for example, when we are generating the false token, we expand the receptive fields of every existing keys to the most recent tokens. A natural question is, so should we expand the receptive fields of query key or vector? This is the same reason with why we are using KV cache instead of Q cache. Because Q is only used to generate the current token, and we dispose of it after we use it. However, keys are multiplied by the queries of every subsequent tokens. And this is same for value. So it's since we are designing an autoregressive model, we cannot change what we have already generated. So it's meaningless to change Q after we use it. However, if we update key and values, when these keys are multiplied by the queries from subsequent tokens, we can make the attention scores from subsequent tokens more accurate. Uh, why we are updating keys rather than values in this work? First is we are updating keys. We have an equivalent form which enables more efficient parallel training. We are updating values. We also have an equivalent form, but this form is like two low rank matrix, but both matrix are passed through a nonlinear activation function before they are multiplied together. So I don't have a method to parallel the training in this case. So we focus on updating keys. And another reason is actually the attention mechanism is mixed information from different tokens. If we have accurate enough attention scores, even if every value vector only contains information from this single token, we can still get a good output. So our method is to keep updating the keys as the context unfolds. And to improve the training efficiency, we cannot materialize this every updated keys at each position. So this is a very important question, as is why there's no information leakage in our method. So first, we will define our method in a recurrent form. So we are generating the T+1 token. We update the keys of existing keys with information from token 1 to token T. So no information after from tokens which are not yet generated is exposed. And when we are generating each token, we update all existing keys. Like when we are generating T+1 token, we update the lookahead keys from using information from token 1 to token T. And we are generating a T+2 token. We generate another group of lookahead keys which contain information from token 1 to token T+1. We do not change what we already generate. Like after we update the lookahead keys with information from token 1 to token T+1, we do not change token T+1. We only use these lookahead keys to generate token T+2. Next, I will provide the definition in current form, so which is naturally autoregressive and with no information leakage. So on the right side is the standard causal attention. On the left is our definition. We have two differences. The first is despite the causal keys in standard causal attention, we introduce another group of keys that are called lookahead keys. I will give the definition of this UT later. Why I use you here is because we are updating these keys as context unfolds. And we combine them together before we pass them through the softmax. And the rest parts are exactly the same with standard causal attention. The formal definitions is like this. Before I explain why we define it like this, I should first introduce some failed attempts. First, I define it in this way because I want to combine information from token 1 to token T. So a very natural choice is to use a bidirectional attention from token 1 to token T. So this is just exactly the same as we are applying a bidirectional attention from the interval token 1 to token T. However, I have very severe numerical instability problem in this case. It will show like not a number after like 50 steps. If I write good kernels, this problem may be solved, but I'm not sure because then to solve this, I use sigmoid directly, and it performs really well. Another reason is softmax forces all tokens to contain information after it, all keys. For example, when you are generating the 10th token, the keys of the second token is forced to contain information from like token 3 to token 9. But this is unnecessary. Like for many auxiliary words, it's unnecessary. And I think this is the process to incorporate information after it. Should like a gate, we decide to how much information we incorporate with it from the relation between this token and token after it. So to solve numerical problem and due to this consideration, I replace the softmax by sigmoid. But now I find the training is very unstable. It will blow up like 300 or 500 steps. It's very unstable. To stabilize the training, I use a hybrid strategy. That is, I use half of the keys, the same as the keys in causal attention. We call them causal keys. And another half is Lookahead keys in this definition. But even in this case, its performance is still worse than the baseline. I was stuck here for some time. Then I consider why it's worse than baseline. I guess the reason may be the way the model extract features from subsequent tokens is different from the way the model extract tokens from features from tokens before it. So then I add a mask here. In Lookahead keys, I only let it see the information after it. For example, the first keys can only see information from the token 2 to the current token. And the fourth token can only see the information from token 5 to the current token without seeing the token information, the representation before it. So in this way, our method finally outperforms the baseline. The definition of causal key is exactly the same as standard definition. And even with this definition, the Lookahead keys which can only see the information after it, if we do not use the hybrid strategy, we only use Lookahead keys without causal keys, the performance is very bad. So to compare the causal keys and Lookahead keys, so the standard definition of causal keys, they're just projection of xt. So they only contains information of each xt. And since from the second layer, since the attention already mixed information, so each separate field is from token 1 to itself. And Lookahead keys from definition, like the Lookahead key of token 2 is a combination of information from x3 to x5. And since we are attention from second layer, since we already have attention in this first layer, so it can see all the information from existing tokens. And since we on the diagonal we use minus infinity, so by definition, the most recent Lookahead key is R0, so it contains no information.
I have a quick question. Why do you mask out the diagonal entries?
This is because the motivation to add this mask is to separate the process of extracting features from like we're defining the Lookahead keys of token I. We are separating the process of extracting features from token 1 to token I, and to token I plus 1 to the token T. We are generating token T plus 1. So I use infinity here to make them separate completely. I also tested if there's 0 here. If I use, in this case, they overlap on the diagonal, and The performance is very similar, but slightly worse than using infinity on the diagonal. So our test, it's the best if we separate them completely. So this is the definition of our tension mechanism. So we add the lookahead keys here and combine them together before we pass them through the softmax. So here is an illustration. So we have two groups of QKV. The first group of QKV are used to generate the lookahead keys with a module very similar to attention. But difference is we use sigmoid and our mask is symmetric to the causal mask. We only let it see the information after it. Then we combine the tension scores together, compute the tension weight, and times VC to get our output. We also consider to add a window on the mask of lookahead keys here. That's because we think the representation of a token may have a limit as a context progresses. In this way, we only let the lookahead keys sees information like if the window size is like 256, each token can only see at most 256 tokens after it. Because we think as a context progress, as the representation of the tokens have a limit, and the information after it may be just noise. And another thing is this can improve efficiency in practice, can reduce computation cost, and also reduce KP cache. In our application study, our model is insensitive to the window size. The performance are very similar in the range 128 to 1024. If the window size is 64, it may blow up. Its performance bad. And for small models, 124 is the best. And for larger models, there's a slight tendency that larger window size could be better. This is reasonable because for small models, its representation capacity is limited. It may only have the capacity to focus on local features. So let it see information much far from it may not be useful. And the reason we use CLU in softmax is to stabilize the training. Without CLU here, for XL models, it may blow up. But for small, medium, large models with window size like 512, the training, the training, I think I remember the result is similar to without this CLU function. So now it comes the most important problem. That is, if we materialize all these lookahead keys, our complexity will be cubic, which is unaffordable. So we have to design an efficient way to train the model. As you can see, in our definition, our okay, let's revisit the definition. UT is multiplied by QT. And in the definition of UT, it's a nonlinear. This matrix, although it's a low rank matrix, but it passes through a nonlinear activation function. So we have nothing to do with this dense matrix. So it's a dense matrix times VC. So equivalently, we can first multiply VU there, multiply VU by QC here, and then times this dense matrix. And this mask is because here in the definition, this vector is t-dimensional. However, this matrix L by L is 6 lengths, so we add this mask here. The detailed proofs in the paper. So now we have two matrices. This matrix, there's a nonlinear function here, so we have nothing to do with it. But this matrix is a low rank matrix times the mask. So to reduce the computational cost, we can utilize this low rank structure. For example, SU is the attention score generated by Lookahead keys. As we have discussed, it's a multiplication between the two matrices. So for this block, blue block, we can first times VT1, this VUT1 with this blue triangle, and then sum the multiplication of this yellow triangle of this yellow block. Since the blocks on the same column are using the same VU block, so this part, like VUT1 times this blue triangle, can be reused again for this green block. The difference is for this blue block, it's multiplied by UCT2 on the left, and for the green block, it is multiplied by QCT3 on the left. But this part, like VUT1 multiplied by this blue triangle, can be reused again. We do not need to compute it again. We just we only need to store it here as an auxiliary variable. Then we continue the process. For this green block, we also compute the VUT2 multiplied by this green block, and we sum them together. Then for this pink block, we only need to compute this pink block. And this blue block and yellow block are already computed. We only need to time this by QCT4 on the left. So for each block, we only need to do one matrix multiplication, one new matrix multiplication, and the other parts can be reused, and a multiplication among a triangular block with a corresponding block. Yeah. This is the formula. So we first update the auxiliary variable. This auxiliary variable, for example, for this block, it is the blue block times this blue triangle. For this green block, that auxiliary variable D is this blue block times triangle plus this green block times this green block. They sum together. So for each block, we only have a constant number of matrix multiplication. And since for this is a part of flash attention, we need to use online softmax. I found atomic aid in Triton is slow in some cases, so it's better to only update one block on the same row in the online softmax. Since in our definition in our method to reduce the computational cost, the columns should be sequential. So at one time, we can only compute one block on the same column on the same row. So to parallel the training, we launch the kernels in the diagonal first, and then the first off diagonal, then the second off diagonal. So in this case, at any time, we will have one block on each row and each column. So this is what we did for training. For inference, it's very similar to the definition in our recurrent form. The difference is we can simplify the computation or the updating step of UT by a runtime update from the definition. If we are using softmax in UT there, we also have a similar updating rule, but slightly complicated than this. It's like updating. We have runtime update on the denominator, and numerator is store some sum. We also update it, and with the numerators divided by sum. But we can do it in a similar way for softmax, but because there's a denominator, so softmax have some numerical instability as we have discussed. But it's also possible to have an efficient inference and training method for both sigmoid and softmax. And I guess the best way may be some combination of sigmoid and softmax in future research, because in sigmoid there's no computation among the tokens from future. And the second step is the combining step. These are exactly the same with in the recurrent definition. The counterpart of KV cache in our method is in the updating step. Obviously we need to store U, and then we store Q. And the combining steps, we store the KC and VC. And KU and VU and QC can be disposed of. These are some experimental results. Our we test our method based on standard llama architecture, and to align the number of parameters, since we combine, we cut the number of heads almost by half. So the projection matrix has almost half number of parameters. To align the number of parameters, we slightly increase the number of heads. And in all cases, Causal has less number of parameters than the baseline. The improvement in the loss is very significant for medium, large, and XL models. For small models, it's like only like 0.01, not that significant as like XL model. For XL model, the improvement in loss is like 0.035. I guess the reason is like the small models is only able to like find some local patterns, so that is see more information from future tokens may not help. This comparison of improvement in small models and XL models. And after we add sliding windows on the Lookahead keys, at least let me revisit the definition of Lookahead keys with sliding windows. Like we only let each token see the information, for example, at most 512 tokens after it. This can help improve efficiency and reduce KV cache. Because if we have a sliding window here, we do not, for Q, we only need to store the size of window size. We do not need to store all the past Qs for QU. And the performance is very close to the case when we are not using the sliding window here, in the sliding window in the Lookahead keys. And downstream tasks improve the average accuracy in all cases. And since to align the number of parameters, we increase the number of keys to have a very fair comparison. We also test the case when we reduce the number of keys. But in this case, the number of parameters in Causal is much less than the baseline. But even in these cases, we still have significant improvement in training loss and validation loss. That's all for my presentation. Thank you so much. Does anyone have any questions?
I had like one question at the end of my little summary there. Just like sort of if you could talk about how extensible this is to sort of even richer dynamic memories.
Like this. Do you mean how we adjust the window size, or?
That could be one idea for sure.
Oh yeah. Uh, our method is not sensitive to window size. We have an evaluation study here. Yeah, the loss is very close in all cases, and I think looking looking at the information, for example, look at Causal token I. Get information from token 1 to token I is different from getting information from token I plus 1 to the current token. From as the context progresses, I think the representation of token may have a limit. So we do not need to see information too far from it. So in our test, the performance is very close after we hit the standard window in the Lookahead keys. And after we apply sliding window to Lookahead keys, we do not need to store the entire queue. We only need to store as many queue as the window size. But the other parts like U, K, V should be the same. We also tested this case, like we stack Causal with standard causal attention, like 3 layers of Causal or 1 layer of standard causal attention, or 3 layers of standard causal attention, 1 layer of Causal. But the performance is very bad. It's much better than both baseline and Causal. So this may be because the representation, the distribution of representations in Causal and the standard causal attention is very different. But it is possible to have a hybrid of different window size in Causal. Like the first layer of Causal use like window size 128, and second the full window size in the Lookahead keys. This is possible.
Thanks for the great talk. I had a related question, which is just a follow-up on, I think, John's question or Jeff's question, which was he had mentioned that this is largely like subtractive against the normal attention score for the original key. And if that's the case, are there other extensions you can imagine that are somehow not purely subtractive?
Yes.
Like if you wanted to, consider something more because of something you learn about it in the future rather than just be able to consider it less.
Do you mean to remove a CLU function here?
Yeah, possibly, or
Oh yeah.
maybe even have a different way of evaluating addition than subtraction.
Yeah. So first, in our first test, we do not do it in this way. Our definition is STC minus STU divided by like the window size. In this way, with or without salute doesn't matter. The performance is very close. But after I remove the division by window size in STU, if I do not use salute here, it will blow up in Excel mode, but it's good for small, medium, and large. And compare whether we divide STU by window size. The loss is better if I do not divide it by the window size in the early stage, but very close, but only slightly better if I do not divide it by the window size at the end. But since we do not divide it by the window size, when we do not divide it by window size, the loss is slightly better. So I choose this method. So if I do not use Silu, I can stabilize the training by times a small constant with STU here. So this is possible. This is possible. And I think for larger models, it doesn't matter if I remove Silu and times a small constant by STU here to stabilize the training.
And do you think that could improve performance, or it doesn't seem like it really changes anything?
For model like 1.3 billion parameters, divided by the window size, but do not use Silu, has slightly worse loss cases. We use Silu here, but do not divide it by slightly window size. But I think for larger models, it may be better because it can incorporate information after it, and the larger models have better representation capability. It is possible.
Gotcha. So it sounds like it's sort of a question of figuring out whether there's a stable way to keep it high performing but still work. Cool. All right, thank you.
Okay. Does anyone have any questions?
And can you go back to the slides where you mentioned like the stability? So you need sigmoid function to stabilize.
Okay. Yeah.
Can you explain it again why you need a sigmoid function?
Results. Sorry. Yeah. For okay. Yeah. My first trial is using softmax here, but it has very severe numerical instability. If you show not a number, like after 50 steps. Because we can also derive a similar equivalent parallel form, like this. But for softmax, we have another denominator which can be very small. It may help if we write good kernels for it, but for training kernel for this version of sigmoid version, it's already over 2,000 lines. So it may worth trying. I will leave it for future work.
Do you have any plan to open source the code?
We cannot release it now due to the confidentiality policy. We may apply
In the future.
in future. We may, but I'm not sure.
I see.
I have another question. I've been thinking about some ideas regarding the idea of recontextualizing parts of the input stream again in transformers. And I guess my question is, do you think that it would create a similar result if you just took the window size that you have and like say repeated the input stream every every time that happened. So that essentially that would be like a mechanical way of allowing the same inputs to see what happened after them by looking backwards, if you see what I'm saying. Instead
Yeah.
of adding a new way of looking forwards, do you think there are sort of input stream ways of creating the same effect by repeating things that came in?
Yeah, I was thinking similar way to like echo embedding. It just duplicates the input. I guess so, but this can increase the synchronous and increase the training cost. But because after adding the setting window here, our training costs very close to standard causal attention. But if we duplicate the input, it increases the synchronous.
Gotcha. Thank you.
Okay, any further questions? It seems that we don't have further questions, so let's wrap it here. And thank you for the presentation.
Thank you so much. Thank you so much. Thank you.
Thank you.